Welcome to the discussion. Today we're diving headfirst into the 2024 Nobel Prize in Chemistry, awarded for groundbreaking work in protein structure prediction and design. Ready to unravel the secrets of proteins?
Absolutely. This year's prize highlights a truly remarkable convergence of computational power, artificial intelligence, and fundamental biochemistry. We're talking about predicting the 3D structure of proteins and even designing entirely new ones, something previously considered science fiction.
Let's start with the prediction side. Demis, Hassabis, and John Jumper used AI to predict the structure of almost all known proteins. How did they pull that off? Was it just brute force computing power?
Not just brute force, but a clever application of AI, specifically AlphaFold 2. They leveraged deep learning, particularly transformer neural networks, to identify patterns in massive data sets of known protein structures and amino acid sequences. This allowed AlphaFold 2 to learn the complex relationships between a protein's amino acid sequence and its 3D structure, making accurate predictions.
So AlphaFold 2 essentially learned the rules of protein folding. That's mind-blowing. What was the significance of using transformer networks?
Exactly. Transformers excel at processing sequential data and identifying long-range dependencies, crucial for understanding how a long chain of amino acids folds into a specific 3D shape. Previous methods struggled with this complexity.
And the accuracy. How close were their predictions to experimentally determined structures?
Astonishingly close. AlphaFold 2 achieved an accuracy comparable to experimental methods like X-ray crystallography, a huge leap forward. This has revolutionized the field, making protein structure prediction readily accessible to researchers worldwide.
Let's shift gears to the design aspect. David Baker's work focuses on creating entirely new proteins. How does that even work? Is it like designing a molecule with a specific shape?
It's more sophisticated than just designing a shape. Baker's Rosetta software uses a reverse engineering approach. Researchers input a desired 3D structure, and Rosetta predicts the amino acid sequence that would fold into that structure. It's like designing a building and then figuring out the blueprint.
That's incredibly elegant. What are some potential applications of this protein design technology?
The possibilities are vast. We're talking about designing proteins for targeted drug delivery, creating new materials with specific properties, developing more effective vaccines, and even engineering enzymes to break down pollutants.
So we're talking about a potential revolution in medicine, materials science, and environmental remediation?
Precisely. The ability to design proteins with specific functions opens up a whole new world of possibilities.
Let's go back to AlphaFold 2 for a moment. The fact that the code is publicly available is a game changer, right?
Absolutely. This democratizes access to protein structure prediction, accelerating research across various fields. Millions of researchers are now using AlphaFold 2, dramatically speeding up their work.
What about the limitations? Is AlphaFold 2 perfect?
No technology is perfect. AlphaFold 2 can still struggle with some particularly complex proteins, and the predictions aren't always 100% accurate. However, the software provides confidence scores, allowing researchers to assess the reliability of its predictions.
So it's a powerful tool, but researchers still need to exercise critical judgment.
Exactly. It's a powerful tool that significantly accelerates research, but it's not a replacement for experimental validation.
Looking ahead, what are the next big challenges in protein structure, prediction, and design?
One major challenge is improving the accuracy and efficiency of predictions for particularly challenging proteins. Another is integrating AlphaFold 2 and Rosetta to design proteins with even more complex functions.
And the ethical considerations, are there any potential downsides to this technology?
As with any powerful technology, there are ethical considerations. For example, the potential for misuse in bioweapons development needs careful consideration. Responsible development and regulation are crucial.
This has been a fascinating discussion. Thank you for shedding light on this groundbreaking work. The future of protein science looks incredibly bright.